Hi everyone, my name is Lydia, and this is what I wish they taught me about econometrics and introduction. We've seen the intuition, derived the formula, so let's put numbers in and calculate exactly how much attenuation bias occurs. By the end of this video, you'll be able to quantify attenuation bias from first principles, just from knowing the true variance and the measurement error variance. Suppose that the model that we are trying to estimate is something like income equal to 20 plus 4 times education plus an error term. Keep in mind here, I am not using predicted income. I'm saying income is 20 plus 4 education and an error term. So the true causal effect, the beta 1 hat, is 4. Which means every additional year of education increases annual income by £4,000, let's say. This is what we want to recover, but education is measured with error. So OLS will fall short. Education, let's say, is self-reported in a survey. People estimate rather than check their records. From the data, we know true variance of education, let's say sigma square x, and we can put the star because we talked and we assigned the star to the true values. So the true one is 9, and the measurement error variance, let's assume sigma square v equal to 3. So measurement error variance. The observed education variable contains both the genuine variance and the random noise. So these 9 in here, that's your real signal. And the 3 is basically your noise. Notice that the ratio that we have here, the noise is 1/3 of the true signal. Now, that sounds manageable, but as you'll see, it still causes a meaningful bias. So let's write the formula for the attenuation factor, which we know is sigma squared, the true one of the x, divided by the sum of sigma square x, the true one, plus sigma square of the measurement error. So from here, we have that this is 9 divided by 9 plus 3, which is 0.75. Okay? So the attenuation factor is 0.75. Now, here's the best way to interpret this. 75% of the observed variation in education is genuine signal, which means the 25% that remains, that's your measurement error. Since OLS cannot distinguish between the two, it only recovers this 75% of the true effect, which means the other 25% is lost to noise. Now, this is the reliability ratio interpretation. And keep in mind, the attenuation factor tells you what fraction of the observed variation in X is real. So the higher that fraction, the less bias, and the lower that fraction, the more bias. So if we apply the attenuation formula, our beta 1 hat would be beta 1 times the attenuation factor. So we found that the true one was 4 times 0.75 would mean that we would end up estimating a beta 1 that is 3 when we take education with measurement error. Okay, so this is what the OLS would give with education with measurement error. Okay, So the coefficient has been pulled towards zero by exactly 25%. Now, the relationship per se hasn't disappeared. It's just been weakened. OLS sees a real relationship between education and income, but it underestimates it because part of what it's calling variation in education is actually measurement error that has nothing to do with income. So again, getting back to that, it's this noise. And in terms of practical costs, keep in mind the true return to education, we said it's 5,000 per year, but based on noisy data, we'd conclude that it's actually 3,000, which means that's a 1,000 underestimate per year of schooling. So if you think about it, that's actually large enough to matter for policy. If we were to compare different levels of measurement error, if we look at this table right here, you can see that as measurement error increases, meaning you see your sigma square of the V, so the noise increasing, the attenuation, so in this direction, we're increasing the noise, attenuation factor actually is falling down. So in this direction is falling down. And the estimated coefficient is also shrinking in this direction until we get closer to zero. Okay. So for instance, at sigma square, V being 9, so this point right here, we very clearly see that the noise is equal to the signal. We have like the signal drowned entirely in the noise. The estimates collapses to zero. Okay. So a larger sample with some noisy measure gives you the same attenuated coefficient, just estimated more precisely. But in any case, even larger sample sizes still do not manage to help you recover from measurement error. Now, why this matters for real decisions? Again, imagine the policymaker using noisy survey data to evaluate the return to education. And as we said in here, we would have estimated the beta as 3. So imagine a true effect where you have 4,000 pounds per extra year of education versus now the 3,000 pounds that we are estimating with bias, okay? The investment in education here is very much underestimated. Okay, so measurement error doesn't just affect statistical estimates, but it shapes real world decisions. So this is why also economists invest heavily in administrative data so that everything is recorded properly. Okay. Overall, the key takeaway that you have from here is that with the attenuation factor, you can check how much of the actual true effect is drowned by the noise. And then you can sort of see how much this measurement error in X pulls the coefficient towards zero. And the attenuation factor tells you exactly how far towards zero that pull is. Okay. I hope this video was helpful to give you a better insight on how exactly the attenuation bias is affecting your betas. Stay tuned, and I'll see you in the next video.